Today's topic is infill prestressed concrete bridges. I will start firstly with a small introduction, followed by an explanation of what we are going to model today, and followed afterwards a live demonstration, and at the end we can go through a live Q&A session. Firstly, this type of ridges are designed, the beams for this type of ridges are designed so that they act alone under their own self-weight and the wet concrete load. At transfer, there is a need for a compression flange only at the bottom, or at the soffit, leading to the very common use of inverted T-sections. Once the concrete hardens, as you know, the concrete part from the slab offers the compression flange for the composite section. There are some advantages to this type of bridges, such as the need for a reduced quantity of formwork, as the beams act as permanent formwork for the slab. Also, with this type of bridges, there is a need for a smaller height of the section, leading to more headroom under the bridge. And also, these type of bridges have a very large stiffness, and it may be a good solution when it comes to strict codes for vibration or deformation rules. In today's example, I will model a bridge that has 15 filler beams at 0.75 meter centers with one edge beam on either side. The length of the bridge is 16 meters and the width of the grillage model is 12. Transverse elements are spaced at 1 meters, with the abutments being 1 meter in thickness and having a height of 4 meters. And the piles will be 10 meters long. This is how the model will look, and now I'll go straight into modeling. We have to first start by defining some materials and some sections. We can define the materials easily from the material properties. I'll just add the material for, say, the beams. So 4050, C4050, we can choose one from the database directly. Now for this type of sections, we can use, these being a composite sections with concrete infill, we can use one of our tools called the sectional property calculator. And I will show you just how easy it is to define this type of sections using this tool. I'm just using the unit system Newton millimeter, and then just using the quick generation tool, I can define such a beam. In the installation folder of Midas Civil, you have a database of all the standard sections, which you can use to define this type of sections, or any composite sections for that matter. So I'll just simply open one of these sections, so TY for solid this time. I'm going to use a TY8, and I'll just assign the slab thickness, the distance to the bottom of the beam, and the width on either side. And now I'm going to define some material properties. For the beam, I will use C4050, modulus of elasticity, and the density. And for the slab, I will use a C3037. This time the modulus of elasticity will be 32836. I can simply assign the beam, the C4050 grade to the beam, and which is part 1, and for part 2 I will keep C3037. Here we can change the mesh size, and we just have to export the section, give it a name, 8, and save. And now the section has been created with the section properties, and now we can just simply close this, go into Midas Civil, choose a composite section, composite general, and import it. And now we have the section imported into Midas Civil. We just need to assign a name, and that's all. For this model I'm using a large number of materials and sections, and so I will just import these from an existing model. So let me first import the materials, and then the sections from the same model, and also the thickness used for the abutments. Now in the tree menu you can see that my materials and my sections have been added. I have a C4050 for my precast girders. For the substructure I'm using C3037 for the slab as well. I have also a weightless material for the transverse elements for the grillage, and the material used for the pre-stressing steel. And for the sections I have an edge beam, one for the left, one for the right, with different offsets. TY8 infill beam, and the edge ones, one for the right, one for the left. 3 sections with the same properties for the cracked sections. Transverse elements for the slab used in the grillage, and the sections for the piles. Now I can directly start the modeling. I will use our base structure wizard. This bridge is 16 meters long, and as we have elements spaced at transverse elements spaced at 1 meters, just use 16 elements and 1 meter. We'll assign the precast material and the TY8 beam. And now you can see I have my beam created. Now I can simply copy these transversely. So I can simply translate on dy 0.75 16 times, and also I can simply extrude these nodes to create the transverse elements. So I'm extruding nodes to line elements, transverse, and transverse section, and this time minus 0.75, again 16 times. And now I have my grillage model. Now I can start assigning the appropriate sections for the longitudinal elements. This is my left edge beam, this is the right edge beam, left TY8 and right TY8. And now I can see that the deck has been all the elements for the deck have the proper elements. Now I can simply copy these elements to create my abutments. I will simply translate them, copying minus 0.79 along Z. This is the height of my section, so 150 plus 750 from the TY8. And now I have these elements here. Now I can simply use these to extrude from line to planar elements. With the substructure material, I have the thickness. I said the abutments will be 4 meters high, so I have minus 1 meter 4 times. Let me just display the thickness here. Okay, now I have this thickness displayed. Now I will simply extrude these nodes to create the piles. Simply select them using the extrude tool from node to line elements, substructure material, and pile, minus 1 10 times. And now I have my entire geometry modeled. Let's now add some time-dependent material properties to our materials. Firstly, let's add the creep and shrinkage properties. We can use one of the codes available, let's say the European. C4050, we need to add FCK, so 40,000 kilonewton meter, and 1 meter for the notional size, as we have a function that already automatically calculates the notional size of each member. And let's do the same for the slab material. We can save this model if you want. C3037, this time 30 kilonewton per square meter, and also the increase in strength. Again, we can use the European formulation, C4050. This time we have to define FCM, so 48,000 kilonewton per square meter. We can see the change in strength with time. We can do the same for the other material, again using the European formulation, C3037. This time we have 38,000 kilonewton per square meter. And as I mentioned, we can select all the elements and calculate automatically the notional size. Now we can see here that the notional size for each member has been calculated. Now we are just left to link these materials together, the creep and shrinkage properties with the base material. So first the precast, the material for the precast beams, and then the one for the substructure and the slab. Now that we are finished with the materials, as you know, the construction stage analysis in Midas Civil is based on the concept of activating and deactivating structure, boundary, and load groups. So now we need to create these groups. I will create one group for each beam. You will see later how this will be helpful. So we have 13 TY8 beams, so TY8 from 1 to 13, then TY8 left, TY8 right, the substructure, the transverse elements, and the edge beams. And we also need boundary groups. I will consider, firstly, let's add the soil springs. I will consider a simply supported condition when the precast beams are added on the abutments, and then we will consider integral condition after the concrete has been poured. And we also need some load groups. I will consider self-weight in this model, wet concrete load, earth pressure, surfacing, and the pretensioning. Now that we have all these groups added, we can start assigning the groups. So let me first activate just TY8 beams, and this will be beam 1, beam 2, 3, 4, 5, 6, 7, 8, 9, 10, and just the last 3 now. 11, 12, 13. and now the left TY 8 and the right one. The substructure, the transverse beam elements, and the edge beams. Now that we have these added and we have material, section properties, and the geometry done, we can start adding boundary conditions. I will first add the soil springs for the piles. We can use the integral bridge function. I will do it for just the piles in this example. Let's say we have stiff clay, ground level is here, the pile diameter is 0.75, subgrade reaction, let's say 80,000, and cohesion, under cohesion 100 and let's say 110. Now I can simply select the piles, make sure I am in the right boundary group, so soil springs, and click apply. And now you can see how all of these springs have been added automatically with different values along the depth. And now let's add the connection between the abutments and the beams themselves. We'll use elastic links for this. Firstly, the simply supported condition. I'm restricting all translational degrees of freedom and torsion. Elastic links have their own coordinate system, internal coordinate system. So restricting SRZ for these links actually will restrict the torsion for these beams. We want to make sure that this won't give any instability when we activate the elements. Again, we can copy this. Say 14 times at 0.75 about y, 14 at 0.75, and we just need to add the two nodes. And on the other end, as I'm releasing sliding, so in this case SDZ can be 0, and we can also define the integral connection here. This time I'm going to use rigid type elastic links, and we have 16 this time, 17 links this time, so 17 copies. And now that we have all the modeling done, boundary conditions, we can start adding some loads. First, let's add the static load cases. Firstly, the self-weight. This is a construction stage load. Then the wet concrete. The earth pressure. The surfacing. And the pre-tension. Now the self-weight will be added using the self-weight function, making sure we are in the right group, acting along Z in the negative direction. Now the wet concrete load, I will add it as UDLs on the main girders. So wet concrete load, say for the TY beams minus 9.6, and for the TY 8E beams, so the edge ones, let's say this is minus 6.2. The surfacing I will just consider the same on all girders, so let's say this is minus 4. Again, making sure we are in the right load case and the right load group name. Now the earth pressure can be easily added on the abutments using the hydrostatic pressure function. I'm going to select earth pressure load case or pressure group name. Let me just isolate these. So I simply have to give a reference level, say the constant intensity, say it's 10, and it increases with a gradient of 5. Now you can see the earth pressure added, and we can do the same on the other end. Now we see the earth pressure acting on the elements. Now in order to add the pretension, we first need to add information for the tendons. We can do that from the tendon property. Let's give this a name, tendon, and this will be internal pretension. Material, as I've mentioned before, I have defined a material for the tendons, and let's add tendon area. Strand diameter is calculated automatically. Let's consider relaxation and the ultimate strength and the yield strength. Now to add in the tendons, I will use one of our functions called the tendon template. Now you will see how these can be very helpful, how the groups can be very helpful. Now I have one beam selected. I can use the auto generation tool. The software will automatically recognize what type of section this is, and I can see now all the tendons added. I can select these, delete, modify, do whatever I want with the profile itself. If I want to consider debonding, I can simply select a strand, click modify, and from here I can play around with these options, with the offset. Now I can simply click apply, do the same for the second beam, for the third one, for the fourth, the fifth, sixth, the seventh beam, beam number 8, 9, 10, 11, 12, and the last one. And for the edge beams, again, the auto generation will recognize what type of beam I have. The same for the other one. And now I have all the tendons added. Let me show you the tendons. Now I can see all the tendons in my elements. Now we can add the pretension load. Again, the pre-stress in the correct load case and the correct load group. I can select the strands, select if I want to add it as a stress value or as a force, where to add it, and click add, and now the pretension force has been added to the sections. Now, as I've mentioned before, I will consider crack section as well. So now we can add these properties. I'm considering these in cases where the hogging moments will crack basically the slab part. So we can consider this with the software. You will shortly see how this can be considered. The left one and the right one. And now that we have materials, geometry, and loads boundary conditions added, we can define the construction stages. I will consider 3 stages for this model: a default value of 10 days, and we choose to save the results for the stage. In the first stage, I'm activating the substructure at an age of 28 days and the soil strings for these, self-weight and earth pressure. Stage 2, I'm activating the beam, the precast beams. Again, these are precast. I'm considering 28 days of age, and the simply supported condition together with the pre-tension load and the wet concrete load. And the third stage, which is the long-term stage, I am activating the edge beams and the transverse elements. Last stage was 10 days, so I'm considering that these are activated at an age of 10 days. And I'm deactivating the simply supported condition and activating the integral condition, and deactivating the wet concrete load and activating the surfacing load. We can also add information for the composite sections. So the first section, this gets activated in stage 2 at an age of 28 days. And for the slab part, I'm choosing material so that I can assign a specific material to it. If I'm choosing element, this will take the information from the assigned material. This time I'm assigning directly a material to the slab part. These get activated in stage 3, and because stage 2 is 10 days long and my wet concrete load acts for 10 days, when I'm activating the slab part of the composite section, I'm considering this to be 10 days of age. In this way, the material properties such as creep shrinkage and strength will be considered as for 10 days. Click apply. Do the same for the other sections. Again, add the slab material. This gets activated in stage 3 at 10 days. And the same happens with the left one. Precast beam is 28 days when it gets activated. Stage 3, 10 days. And now for the crack section properties. For the crack section properties, I'm activating again 28 days for the beam. The material for the second part, the same slab material, activated in stage 3, 10 days. But this time, to ignore the properties, the moment of inertia and the section properties for this part, as I'm considering cracked, I can simply define these as 0 here, and they will be ignored for the section, or be multiplied with a factor of 0. I'm keeping the weight because I want the weight to be accounted for, and do the same for the other beams, for the other sections. Again, material, slab, stage 3, 10 days, and assign crack section properties. Using 0 means that I'm considering 0 contribution from the slab part for these elements. And now that we have basically finished the modeling and defining the construction stages, we can go through the stages and check that everything is correct. Stage 1, we can see only the substructure activated, self-weight and earth pressure load. Stage 2, precast beams are added with the wet concrete load and the pre-tension load. Stage 3, the beams and transverse elements, precast beams become composite with the slab, and the transverse elements from the slab get activated as well. And I'm deactivating the wet concrete load and activating the surfacing load. And now to this model we can also add moving loads. Let's say we are using the Euro code. We can start defining the traffic lanes. Say lane 1, an eccentricity of -3 meters. This is a grillage model, so we need a crossbeam distribution. And now defining a reference line. Okay, now lane 2. This time eccentricity of 6 meters. Again, crossbeam distribution. Define the reference line. And for lane 3, this time -9 meters. Again, transverse beams for the crossbeam distribution. And now we can start adding some vehicles. We'll use load model 1. So 0.61, 2.2, 2.2 and 2.2. And I will also use an SV vehicle, let's say SV80. And we can define the moving load cases now. Let's consider GR1A first. It will act on all lanes, only load model 1. And GR5, I'm adding the special vehicle and defining the lanes for the straddling. And now everything is defined for the model. In order to save time, I will just open a model that I already have analyzed to show you some results. Here's the model. Let's first check the results for construction stages. Say in stage 1, let's check the deformations. Edge examination. We can see the deformed shape, and we can also check, say, bending moment diagrams for these. Stage 2, same. We can check the bending moment coming from the pre-stress and from the dead load. We can see that we have no hogging bending moments, as this is the simply supported condition. And if we go to stage 3, we can now see that hogging moments appear in our structure, as now we have activated the integral condition, the integral connection between the abutments and the beams. We can also check tendon losses, either in graphic format along the stages, or we can check in table format as well. Here we can choose which strand we're interested in, at what stage, and we can see stresses after the immediate losses, losses due to elastic deformation, creep, shrinkage, and relaxation. And we can also read results directly for composite sections. Say summation, stage 3. And we can see for each element, we can see results for part 1 and results for part 2. And the same goes for the stresses. We can see stresses due to axial force, bending moments in both directions, and stresses at combined stresses at each end of each corner of the section. And we can also read results for moving loads. These are bending moment diagrams for GR1A. These moving load results are enveloped results, so these are the maximum positive bending moments for each of the elements. We can check the minimum ones as well, or we can check both at the same time. And if we want to see the critical vehicle position for any of these results, we can see here, for example, let's take the maximum one. Maximum bending moment occurs in element 120. Using the moving load tracer, we can simply go assign the key element, and we can see the vehicle position that gives the maximum bending moment in this element. We can do the same for GR5, and if we want, we can take these critical vehicle positions and export them into static load cases if we want to combine these with the static load case and having coexisting forces, or also if in the analysis in the moving load analysis control data, we can choose to have normal and concurrent forces calculated for this analysis, and in table format we can simply right click and choose view by max value item, and in this way we can see directly coexisting forces.